Today I'm going to dive a little bit more into the matching code that we saw in class. So hopefully it will make it a little bit more clear. You have the notes in the code, but just for the sake of clarity, let's dive into the example. So we're going to start with the code that we saw for this week. So I'm just going to load everything. One important thing, we're introducing here a new package. It's called Match It, and this is the code, the package, that we're going to use for any of our matching needs. Okay, so as you can see, I have the data set for the get out the vote example that we saw in class, and I'm going to just run these quick lines that are just to clean up the data a little bit. In particular, we're just going to be focused on one specific strata. So as you can see here, we're just focusing on state 1 and a competitive district. So we're going to be working with this smaller sample, which is around 20,000 households. So if you remember, this was a randomized experiment. So we have basically a treatment variable that was randomized, but maybe that is not actually the treatment that we want to find a causal effect for. Okay, remember that maybe what we're interested in is actually what is the effect of someone receiving and actually picking up the phone for a get out the vote call. So to that extent, we are going to use contact now as our new treatment variable. Okay, remember that contact takes the value of 1 if someone actually was contacted by the get out the vote campaign, and 0 if they were not. Okay, so you can think about this as observational data in the sense that this could be a list that the get out the vote campaign has with them. They didn't randomize anything, they just tried to call everyone. Some of them picked up, some of them did not. Okay, so we're trying to get a causal effect out of this. If you remember from class, we discussed that probably comparing people that got contacted but versus those that did not is not a great way to get a causal effect, because people that picked up the phone are very different from people that didn't. We said, for instance, that people that picked up the phone are probably older than people that didn't. That affects both your probability of treatment and also your probability of voting. Older people tend to vote more than younger people. So what can we do about that? We talked about controlling or adjusting for confounders, or potential confounders. And here in our data, we have a lot of them actually. So we have, for example, whether the person is a new registered voter or not. We have their age, which again, it's an important one. We also have their gender, for example, and also their past voting behavior. Probably someone that voted more in the past is more likely to vote now. So we want to adjust for all those things, and we're going to do it through matching. So this is basically the function that we're going to be using to create this match sample, and is the function matchIt. MatchIt basically takes 3 main arguments. The first one, which is this one right here, is a formula. The second one is going to be the data set that we're passing through. And the third one is the method. Okay, so let's go into the formula first. As you can see, I have my treatment variable on the left-hand side, or on the right-hand side if you're looking the other way. On the left-hand side, and on the right-hand side, I have all the potential confounders that I want to adjust for. So I have, again, the number of people that are in the household, past voting behavior, gender, age, and so forth. Okay, this is going to calculate basically our propensity score. Remember, that is the probability of being in the treatment, in this case the probability of getting contacted, given all these characteristics. The second one is pretty self-explanatory, it's just the data frame that we're using. And the third one is the method. In this case, we're using a nearest neighbor method. Okay, this is just the way that that this function is going to go find similar people on the control side. Okay, so we're just using nearest for nearest neighbor. I have 2 additional arguments here that they are actually not necessary. You can add them or not, depending on what way you want to match. Exact, basically what it does is what it says. It exactly matches on one variable. So in this case, for example, I want to exactly match by state. This means that I can only match a treated unit in state A, for example, with a control unit in that same state. Okay. So this is again to control for people that are within specific clusters, for example, or a variable that we really wanted to be like perfectly balanced. And finally, caliper basically is also kind of a boundary argument, in the sense that we don't want to match anyone to anyone because they're just like left there. We want to have certain control over our matched sample. And caliper, what it does is basically sets up a boundary around each individual and says, okay, for a treated individual, I'm just going to look around a neighborhood of 0.2 units, and whichever control unit is closest within that neighborhood, I'm going to match it. But if there's no control unit within that neighborhood, then this treatment unit is going to be left unmatched. That is the idea. Again, we don't need this. We can actually move this. We can set this a more loose boundary to 0.5 or a more strict boundary, 0.1. And you can play around with that. Usually I will give you the caliper that you need to use in the case that you use it. So let's run this, this function. And as you can see, we get a new object that's called M1. M1 has a lot of different things, but let's look at the summary. In the summary, as you can observe here, we basically get two balanced tables. The first one is the balance of all the data, meaning before matching. And the second one is the balance for the matched data, after we did all the matching. Just focus on the first three columns. The first one is the average for the treated group, the second one is the average for the control group, and the third one is the mean difference between the two groups in standard deviation. So that means that I can actually compare this because they're in the same units. So as you can see, we do have certain imbalances, especially for example here in age. It's at 0.2 standard deviation that is usually seen as a big imbalance, right? And probably voting behavior is something that should catch our eye as well. It's again about 0.1. As a rule of thumb, any standardized difference that is over 0.1 standard deviations is usually thought of as something large. Okay, so they're unbalanced, not terribly unbalanced, but they do not look great. But after I match, as you can see, now all of those standardized differences actually reduce substantially. They're all very close to zero, so this means that now my two groups, after matching, look very much like each other, okay? One important thing, as you can see, the mean of the treated group before and after matching doesn't really change that much, and actually in this case doesn't change at all. The treated group stays the same. What will change is our control group. Okay? Our control group first looked very differently, and now it looks much more similar to our treated group. Okay? Finally, one thing that you should note is that we have the sample sizes down here. So you can see that before matching, we had around 19,000 observations in the control group, while after matching, we only get 1,300. Okay, so the same number for treated and control. Great, so we have our matched data. Let's actually transform it into a data frame. How do we do that? With the function matched data. So as you can see here, now I have a new data frame, DM1. As you can see, it's much smaller, has the same number of variables, but it has a few more variables just because it's showing the weights and the distance, meaning the propensity score for each variable. Do not worry too much about that. But it's basically just our matched data set. We can also see how many treatment and control we have in each. So remember that we should have the same number of treated and controls. This is the same, and again, it's the same that we had right here. Okay. With this, we can also build a balance table just as we did for an RCT. So let's just select our covariates and build our balance table. And as you can see, this is basically our new balance table for our matched data. This is again not an RCT, but as you can see, differences are very small. All p-values are very large, so this is good. Our two groups are actually balanced. Okay, great. So how do we actually analyze this? Just as in an RCT, we did all the balancing beforehand, right? So all I need to do now is just run a simple regression between the outcome and the treatment. Remember that the treatment node is the variable content. So let's run this. And this is our estimate. So after matching, assuming that we have control for all observed for all confounders, we can say that actually there is no significant effect for contacting someone in the Get Out the Vote campaign on voter turnout comparing to not contacting someone. Okay, you can see that because the p-value is actually larger than conventional values, so it's closer to 0.2. So there's actually not a significant effect in this case. Okay, so again, assuming that we're controlling for all confounders, then this could be a causal effect. Okay, and again, we find really no evidence of contacting people here. So the main thing is, however, in matching, just as adding variables to regressions, for example, is whether we can safely assume that we're controlling for all confounders. We're controlling for everything that is in our data set, right? But think about whether there is other confounders that are not in our data, that we're not matching on or adjusting for, that potentially could still be confounding variables.